The first question we should probably ask is exactly what do we use detectors for? Well, as the name implies, a detector's first use is the detection of radiation or radioactive material. And sometimes that's all we need to do. An example of this would be using a survey meter, such as a Geiger counter, to look for radioactive contamination, or, as another example, portal monitors to check and make sure no one is walking out the door with a radioactive source. The second thing we use detectors for is identification. And by that, I mean we can actually determine what nuclide is generating the radiation. Examples of this are handheld isotope identifiers. These are spectroscopy detectors, which we'll talk about in a minute. The third thing we can do is quantification. Not only can we identify which isotopes are generating radiation, but we can quantify the amount of each radiation and each radioisotope present. Examples of this would be nuclear material accountability measurements, or the amount of particular isotopes in special nuclear material for forensic analysis. Depending on our interest, each of these tasks gets progressively more difficult to do. We'll consider each of these measurements tasks in this class, but we are most interested in the last one, being able to quantify the amount of a radionuclide that's present. In the case of nuclear materials, we use the unique properties of these materials to allow us to detect, identify, and quantify these materials. The nuclear materials that are of interest to us are uranium and plutonium and the associated minor actinides that come with them, americium, curium, neptunium, and californium. What properties do nuclear materials have that allow us to detect and identify them? Generally, they all emit gamma radiation, and typically these gamma rays are low energy, meaning a few hundred keV or less. They also emit X-rays, which are self-induced by alpha decay. Beta decay are from absorption of gamma radiation, which in turn induces these X-rays. As we said, they emit alpha radiation. As a secondary effect from decay, they emit heat, either in the form of infrared or by conductive flow of this heat from the energy deposition of the decay products into the material matrix. They emit single neutrons from alpha N reactions and from delayed neutrons produced by spontaneous fission. They emit bursts of neutrons from either induced or spontaneous fission. The number of fission neutrons ranges between 0 to 8 per burst. Finally, these special nuclear materials are fissionable and fissile. Fissile means they are able to fission with thermal or very low energy neutrons, and fissionable means that these nuclides will fission with high energy neutrons. An example of fissile material is uranium-235, and an example of a fissionable nuclide is uranium-238. From fission, we have prompt fission neutrons that are formed with 10 to the minus 15th seconds of the fission, delayed neutrons coming milliseconds to tens of seconds after the fission, and prompt and delayed gammas.